Imagine a time when the entire universe was a blindingly hot, opaque fog. We're looking back 13.8 billion years before galaxies, before stars, and before the darkness of space itself existed. This is the era of the Primordial Echo, a moment frozen in time that still surrounds us today, detectable in every direction as a faint microwave hum. For the first 380,000 years after the Big Bang, the cosmos was a seething plasma of protons, electrons, and photons. It was too hot for neutral atoms to form. Light was constantly scattered by free electrons, trapped in a dense glowing cage. The universe was not black, it was a wall of incandescent fire. Then came the epoch of recombination. As space expanded and cooled, the temperature dropped enough for protons to capture electrons, forming the first neutral hydrogen atoms. Suddenly, the fog lifted. Photons, once trapped in that chaotic dance, were finally free to stream across the cosmos, creating the first flash of light. That ancient light has been stretching with the expansion of space for over 13 billion years, shifting from visible light down into the microwave spectrum. We call this the cosmic microwave background, or CMB. It is the oldest electromagnetic radiation in existence, a fossilized snapshot of the infant universe. When we point our most sensitive radio telescopes at the sky, we see this afterglow at a temperature of exactly 2.725 Kelvin, just a fraction above absolute zero. It is incredibly uniform, a perfect blackbody spectrum that provides the strongest evidence we have for the Big Bang model, yet it hides subtle irregularities that define our reality. Buried within this smooth background are tiny temperature fluctuations, variations of less than 1 part in 100,000. These are not random errors, they are the fingerprints of Baryon Acoustic Oscillations, or BAO. Think of them as immense sound waves that rippled through the primordial plasma, driven by the intense pressure of radiation. These acoustic waves compressed matter into denser regions, setting the blueprint for where galaxies would eventually form. When the universe cooled and became transparent, these sound waves were effectively frozen in place, leaving behind concentric rings of higher density matter that astronomers can still detect in the distribution of galaxies today. Cosmologists use these frozen echoes as a standard ruler to measure the expansion history of the universe. By analyzing the scale of these oscillations, we can constrain the properties of dark energy and test the limits of general relativity, probing the very geometry of spacetime itself. Today, facilities like the Simons Observatory are hunting for even fainter signals within the CMB, B-mode polarization. These twisting patterns in the light would be the direct echoes of primordial gravitational waves, shock waves generated during the universe's inflationary fraction of a second, long before the plasma cooled. This research is critical for resolving the cosmic tension, the baffling discrepancy between different measurements of the Hubble constant. By studying the first light, we are trying to reconcile our understanding of particle physics with the large-scale evolution of the cosmos, looking for cracks in the standard model. In a very literal sense, looking at the CMB is like using a time machine. We are seeing the universe as it was in its infancy, a simple, hot soup of particles. But this uniformity presents a mystery. How did we get from a smooth, glowing fog to the complex, clustered universe of stars and galaxies we inhabit now? Following the release of the CMB, the universe plunged into the cosmic dark ages. The background glow faded, and for millions of years, there were no sources of light, only vast, silent clouds of neutral hydrogen gas drifting through the expanding void, waiting for gravity to do its work. Deep within those dark clouds, the seeds sown by the Baryon Acoustic Oscillations began to grow. Gravity started to pull the hydrogen together, overcoming the expansion of space, creating pockets of intense density and heat that would eventually spark the next great epoch of cosmic history. The stage was set for a dramatic transformation. The universe was about to wake up from its dark slumber. In the next episode, we will witness the ignition of the very first nuclear fires, the birth of population 3 stars, and the end of the Dark Ages. For 100 million years after the Big Bang, the cosmos was a silent, suffocating ocean of neutral hydrogen. There were no stars, no galaxies, and no light, only the invisible hand of gravity, slowly pulling the primordial gas into colossal, swirling knots in the crushing dark. Inside these dark halos, density spiked and temperatures climbed, forcing hydrogen atoms to merge in the first nuclear fires. These were population 3 stars, monsters hundreds of times more massive than our sun, burning with a furious ultraviolet intensity that the universe has never seen since. Their sudden ignition marked the cosmic dawn, ending the Dark Ages. Their radiation carved expanding bubbles of ionized plasma through the neutral fog, triggering the epoch of reionization. This phase transition transformed the opaque universe into the transparent, starry expanse we observe today, clearing the view for our telescopes. To witness this ancient epoch, humanity deployed the James Webb Space Telescope, pushing its infrared instruments to the absolute limit. In late 2025, astronomers confirmed the existence of galaxy JWST Z14-0, a structure located at a staggering redshift of greater than 14. This signal originates from just 290 million years after the Big Bang, a time when the universe was in its infancy. The discovery shattered our models of stellar evolution because JWST Z14-0 is far too bright, too massive, and too mature to have formed so quickly under standard theories. This anomaly forces us to consider a radical possibility, that the first stars were not powered by nuclear fusion at all. Theorists suggest we might be looking at dark stars, supermassive clouds of hydrogen heated not by atomic fusion, but by the annihilation of dark matter particles at their cores. Unlike normal stars, dark stars would be cool giants, appearing as infrared beacons millions of times wider than our sun. They wouldn't collapse into black holes immediately, allowing them to grow to impossible sizes, bridging the gap between the first gas clouds and the supermassive black holes we see today. Confirming the existence of dark stars would rewrite the laws of astrophysics, proving that the invisible sector shapes the visible world. To solve this, the scientific community has turned its gaze to the ground, activating the Vera C. Rubin Observatory in the high deserts of Chile. Achieving its own first light in late 2025, the Rubin Observatory has begun the 10-year legacy survey of space and time. It scans the entire southern sky every few nights, mapping billions of galaxies to trace the faint frozen echoes of dark energy's influence on cosmic structure. By analyzing the distribution of these ancient galaxies, we can measure Baryon Acoustic Oscillations, sound waves from the early universe frozen in the distribution of matter. These standard rulers allow us to triangulate the expansion rate of the cosmos and resolve the conflict in the Hubble constant. We are standing at the threshold of a new golden age in cosmology, where the line between particle physics and astronomy dissolves. The light from JWST Z14-0 is not just a picture of the past, it is a laboratory test of general relativity and the nature of dark matter itself. As we peer deeper into the infrared, we are hunting for the ghosts of the first supermassive objects that seeded the galaxies we inhabit. Every photon captured is a piece of evidence in the greatest detective story ever told, revealing the invisible skeleton of our reality. The cosmic dawn was not just the birth of light, it was the moment gravity asserted its dominance over chaos. But as we map these ancient echoes, we must ask if our fundamental understanding of gravity is correct, or if the dark sector holds a stranger truth. To understand how these primordial forces will eventually tear the cosmos apart or crunch it back into oblivion, you need to see the endgame. Subscribe to QuasarQuest and hit the notification bell because in the next episode, we will fast forward to the death of the universe. Today, we enter a revolution in observational capacity, marking a golden age of cosmology where models are finally tested against raw data. We are no longer guessing, we are building the machines to test the limits of general relativity against the actual fabric of the cosmos. High in the Chilean Andes, the Vera C. Rubin Observatory has commenced operations, achieving first light in late 2025. This facility is now undertaking the Legacy Survey of Space and Time, or LSST, a decade-long mission to catalog the dynamic universe with unprecedented speed. Over the next 10 years, the LSST will map billions of galaxies, creating a high-fidelity, three-dimensional time-lapse of the cosmos. This archive allows us to trace the subtle, warping influence of dark energy, revealing how the expansion of the universe has evolved over billions of years. While Rubin surveys the optical spectrum, the Simons Observatory is hunting for the invisible afterglow of the Big Bang. Their instruments search for B-mode polarization in the cosmic microwave background, a faint twisting pattern potentially caused by primordial gravitational waves from the universe's birth. Finding these B-modes would be the smoking gun of cosmic inflation, confirming the exponential expansion from the first fraction of a second. It would bring us closer than ever to witnessing the moment of creation, resolving the physics of the universe when it was smaller than an atom. These ground-based giants are joined by NASA's Roman Space Telescope, launching by 2027 to map the universe from orbit. Roman is calibrated to measure Baryon Acoustic Oscillations, the frozen sounds of pressure waves that rippled through the hot plasma of the infant universe. Using these ancient sound waves as a standard ruler, scientists can measure cosmic distances with precision, slicing through the history of expansion. This data is critical to resolving the cosmic tension, a crisis where different methods for measuring the Hubble constant yield contradictory results. The expansion rate measured from the early universe does not match the rate we observe locally, suggesting a fundamental gap in physics. The combined data from Roman, Rubin, and Simons will force us to either refine the standard model or rewrite the laws of gravity. Our target is the dark sector, the 95% of the universe comprised of dark matter and dark energy that dictates the fate of every galaxy. We cannot see these forces directly, but by observing how they bend light, we reveal the invisible scaffolding of reality. Recent findings, like the confirmation of galaxy Jade's GS-Z14 just 290 million years post-Big Bang, have already forced us to revise our timelines. We must now explain how massive structures coalesced so rapidly, investigating whether the first dark stars were powered by dark matter annihilation. This is the power of fossil light. Because light takes billions of years to traverse the void, every telescope is a time machine. We are not merely observing the cosmos as it is today, we are witnessing the fiery crucible of our origins. As we collect this data, the noise of the universe resolves into a clear signal, bridging the gap between the Big Bang and the present. The answers to the deepest questions of existence, the nature of dark energy and the origin of light, are written in this ancient code. We are the first generation with the capacity to decipher this cosmic autobiography, turning the sky into a laboratory for fundamental physics. By catching these ancient echoes, we finally see the invisible forces that shaped our past and define our ultimate destiny. To understand the fate waiting for this cosmic machinery, subscribe to QuasarQuest and hit the notification bell. In our next episode, we fast forward trillions of years to witness the heat death of the universe and the final lingering light of the last stars.